Here's a question. That RAG pipeline that you just built, does it work when the internet goes down? Because for a lot of pipelines, the answer is no. And that's because the model is an API call, the vector database is cloud hosted. That means the second the network drops, the whole thing stops returning results. And that may be fine if your agent is running natively on the cloud and network drops are not considered a severe issue. But if it's a system that is running on the edge in a factory or in another industrial site, then having full internet dependency is not really a safe production pipeline. So in this video, we're going to build a retrieval pipeline with Actian VectorAI database that runs fully on local hardware. And we're going to ingest documents in, get search results out, all without any requirement of internet. Now, before we write any line of code, let's see where we are headed so everything is clear. This is the pipeline with 3 layers. First, we have ingestion, which takes the raw documents and turns them into vectors. Then we have storage, which holds those vectors in the VectorAI database. And finally, we have retrieval, which takes a query and returns the most similar chunks. Everything inside this box that runs local hardware. So in this demo, we're going to see how you can use VectorAI database to run a query and get ranked document chunks with score without any internet connection. Now let's stay on this diagram for a little longer to make sure that we have a shared understanding of what's going on in each layer. The first ingestion layer does 3 things. It loads the documents from the disk. It splits the documents up in smaller parts that we call chunks, and then it takes those chunks and embeds them using a local embedding model. Now there's a range of embedding models that you can choose from, and these are open source available to you through libraries such as sentence transformers and fast embed. Once you have your embeddings, the second layer is to actually store them in the storage layer, which in this case is VectorAI database. It holds the vectors together with metadata, such as the chunk index and the source document, so that we know exactly where the result came from. And the final layer is the retrieval layer, which takes the natural language query and embeds it using the same local model that you used earlier, so that VectorAI database can use that to retrieve the most similar entries that it has stored. And using the same model on both sides is what makes the similarity meaningful. Now, once the setup is complete, every layer here is going to be running on local hardware. This means that you don't need to deal with any API key, cloud accounts, or external dependencies. And that's the whole point. Now we have prerequisites before we get started. The first one is that VectorAI database needs to be running with Docker in your computer. So we already have a video covering that if you haven't set it up already. So feel free to pause and resume once you have it set up. And in this case, you could either use, for example, sentence transformers, especially if you have GPU on your hardware that you wish to use to accelerate. Otherwise, you can also use fast embed, which is more tailored for edge devices, which will then allow you to run these models on the CPU. And finally, you'll need a folder with documents that you want to ingest into your vector database. In this case, any plain text file will do. And during the setup, when we are downloading these packages and models, is the only time where we'll actually be using the internet. So let's get into the terminal. The first thing that I want to make sure is that my container is running with VectorAI database in it. So I'm gonna go ahead and run docker ps, and there you have it. It's up and running, so that's great. Secondly, I have already created a virtual environment, and in here I have ran pip install fast embed for the embedding library, and then also Actian Vector AI client for the SDK to interact with VectorAI database. So in case you haven't run that, go ahead and run that, or so that you have it, and then we can proceed to the first layer of our diagram, which is ingest the documents. Now, I have a folder here called documents, which contains 3 documents: Edge AI, offline embeddings, and vector database. And these are all short documents describing the topic in question. So we can go ahead and look at the code, what it's actually going to do. And it starts by importing the libraries that we need and defining the name of the collection that we're going to use and the path to where our documents are stored. In the following line, we are going to define the embedding model that we're going to use. And in our case, we're going to use All Mini LM L6 V2, which is a great model for short documents. And in the next section, we're going to look at the actual chunking function. And this is quite interesting because this is a word-based chunker, so quite a simple one, which creates chunks of 120 words with an overlap of 10%, so 12 words on each side of the chunk, so the semantic meaning is not lost at the boundaries. Now, an interesting question here is, why don't you just embed the entire document? And the reason for that is, if you were to embed the entire document, a lot of the complexities and the semantic signals in the document would get lost with the embedding. However, if you chunk up the document, that means to break it up into smaller pieces before you embed them, then the semantic signal that you're looking for becomes much easier to retrieve, and that's how you get higher signal retrieval. Now, in the main function, that's where it all comes together. We read the documents that you have in your folder, and for each of them, you run the chunk text function. Now, here, two lists gets created. A list of chunks that is called text, and you also have the source list, which contains the metadata of each chunk. That means that you know for each chunk which source document did it come from, and also within that source document, which chunk am I actually looking at, so that you know where in the document this passage is actually originating from. Those chunks are turned into embeddings by using model.embed. And finally, all of it comes together in this point list, which creates a list of point struct objects, which contains not only the embeddings themselves, but provides an ID for each vector and also the metadata that we just discussed, so that it all comes together in your database. In the next section, we actually transition into the second layer of the diagram that we looked at, which is the storage layer, because here we create a VectorAI client, which ensures that the collection that we're looking at is actually existing. And this upsert function checks the vector ID. So if it already exists, it only updates the vectors instead of reduplicating them within the database. And this way it becomes safe to run the script multiple times. Without further ado, let's go ahead and run this. And here you see the 3 documents have become 6 chunks. And you can easily verify that these chunks have been properly stored in your database by looking at the UI and opening up the collection and checking out the data browser, where you will get a preview of how the chunks actually look. So now that the embeddings are stored, the next step is the final layer of the diagram, which is the retrieval. So let's go into the retrieve file here to look at the code. It starts the same way. We import the libraries that we need and define the same collection that we have originally stored our chunks in. And in the next line, we're going to define the text embedding model again. And here it's important to use the same model that you used in the previous step to ensure that the similarities in between vectors make sense. Then we have a support function here to embed the query by using this model, and a retrieve function, which runs the search on the collection by embedding the query itself. And the limit here defines how many chunks this search is actually going to retrieve for you. And the results here are then being printed based on the payload. And finally here we define a main function in which you can pass the query in the terminal. And the default question here then becomes, how does offline retrieval work, which is relevant to the documents that we have uploaded. So I'm going to go in here and I'm going to just turn off my Wi-Fi. We could also ping google.com and that should probably give us an error. There we go. So with that, let's test running the code. And here you see, we get 5 results on the retrieval with the scores. And you see that the first top 2 already mention the word specifically offline retrieval, and they get ranked by the score. And here, interesting enough, you can see that the payload that comes together with the embedding contains the information about which source document did this actually come from and which chunk is this within the text. So that also allows you to identify where in the documents you see this. And there it is, ranked results, scores, and metadata, all running on your local hardware. So let's recap what we built. An ingestion layer that loads chunks and embeds documents with local model, storage and VectorAI database with metadata on every vector, and a retrieval function that embeds a query and returns ranked results. And we proved that it all works even when the network is disabled. And that's because every component here runs on local hardware with no API keys, no cloud accounts, and no external dependencies.
If you're ready to start building, make sure to not miss a sign up where you can get 1 million vector embeddings for free for 30 days.
And we also have a Discord link that's in the description down below. In the next video, we're taking things to the cloud and we're going to look at how we can use VectorAI database on AWS. See you there.